Hey guys, in this tutorial we will create this procedural tree generator here, and it is based on this geometry node tree here and procedural shaders, and this is only one method on how to do this. There are multiple ways of achieving this, and tree generation is an endless complex topic, and I've maybe done 30 to 40 different methods in the past. And this method here is kind of special because it is based completely on curves. And yeah, so this is kind of like a spontaneous and complex tutorial. So it is really long and confusing at times, but yeah, bear with me and let's start. Before we start, I want to talk about two principles our tree generator will be based on, and we will create a node group for this. And this specifically is the random distribution of points on curves. And I have a tutorial on my channel about this topic, but I will go over it in this tutorial too. And the second thing is to transfer attributes between these curves. Okay, so now let's start. We need to create a curve. Doesn't really matter. Maybe we take a spiral. And to distribute points on it, we need some points. And now we need a sample curve node. And we sample our curve and transfer the position to these points. So we take a set position node and transfer this position to these points. And now this node here is set to vector. If we change the vector, you can see that this point moves along the curve. So maybe to make it a little bit better visible, we can take a join geometry node. So now you can see it a little bit better. And you see this point moves along this curve. And the trick now is to take a random value node in the range of 0 to 1 and plug it in the vector. And now you can see that the point gets placed randomly on this curve. And if we increase the count, each of these points has a random seed. So the cool thing about this method is here that we can define a range with this random value node. And this is exactly what we need for our tree generator. But there is a little problem with this, and I will show you. Here I've created an array of lines, and you can see that the distribution of points only happens on the first line. So we can solve this by toggle all curves, but now the range doesn't work anymore. And this is because the factor here kind of like describes the sum of all of these factors of these curves combined, but we want it to be individual for each of these curves. And we can solve this by remove the toggle here and by working with the curve index. So the idea here is to take another random value node and randomly choose a line. So what we need is the total amount of lines, and we can get it with the domain size node. And here we set this to curve, and this gives us the total spline count. And if we plug this in the max value, we have to remember that the curve index starts with 0 and the spline count starts by 1. So we need to subtract 1 from it. Let me remove the auto offset. And now we can plug this value in the curve index. And you can see that it starts to work. So if we increase the point count, we can now define a range. Yeah, so let's create a node group out of this. So we need the top nodes here. Create a node group. I name my inputs. So maybe we create an input for the seed. And what I like to do is I create an individual seed for each of my random value nodes. And I do this by simply add some random value to it for each seed. Then let's create inputs for the range. So the start and end range. Then also an input for the point count. Yeah. What we also want to transfer is the tangent and the normal. And let's do this. And also we can choose a value which we will transfer. And I also pass this through the output. And I want to create an input for this too. So we can choose outside of this node which value we want to transfer. Let's name this node distribute points on curve. Okay. Now just a little cleanup. I create some default values. So for the start range 0 and for the end range 1, and I also clamp it in the range of 0 to 1. The seed I default to 0 and the count maybe to 25. So yeah. Now we have the distribute points on curves node. The next thing I want to talk about is the transferring of attributes. And this is really important for our tree. So let me show you what I mean by it. So let's imagine that these are some branches that are instanced on our trunk. And let me quickly take my trunk geometry. So yeah, take some imagination. Maybe I increase the height a little bit. Okay, so if we now solidify these curves with the curve to mesh node, and we take a profile curve, so for example, a curve circle would work perfectly. Then we take a set radius node to control the thickness of these branches and the trunk. And yeah, it starts to work. And now to scale it along the curve, one would normally use the curve parameter node or spline parameter with the factor. And we need to invert it. So what I like to do is simply subtract it from 1. And to control the thickness, we multiply it with a value. And now a problem is obvious, and this is the scaling of branches. So we want the branches to scale along the branch or the trunk they get instanced on. So they should normally get a little bit thinner here at the top. And for this I want to transfer the factor of the first curve to the instances. And luckily we can do this with our distribute points on curves node with this value input we pass through it. So let me put this distribute points on curves node to use. So here we have our curve line and we want to distribute some branches on it. Now I have all these points. I decrease the count a little bit. And I want to use these points for my instance on points node. And let's have a look what it looks like. Yeah, looks good. I choose a seed, which kind of works for me. Define the range. And now I want to transfer the parameter of the first curve to these instances. So let's do this. Spline parameter, factor. And now I store this factor here onto my points. So I use the store named attribute node. I name this for factor. And now this attribute is stored in my points and get passed to all the instances. So right here, now I should be able to get this attribute. So named attribute, I choose factor. And now if I multiply this whole thing here with this factor, you can kind of see that the scaling does happen, but in the wrong direction. And this is because the factor here, we have to invert it. So subtract it from 1. And that's the first step. And the second step is that you can see that the trunk disappeared. And this is because we multiply it with the factor the trunk doesn't have. So yeah, the factor here by default is 0. So we also need to store the attribute on the trunk. And in this case, we simply set it to 1. Also, we name it factor. And now you can see what happens. And this is exactly the result we want. So now we can randomize this value here again. Define a start and end range. Okay, so now it starts to begin to look like a tree. And let me quickly, just to demonstrate the distribution of points with the transferring attributes, let me quickly instance some other branches onto these branches here. So maybe I copy this whole setup. And we want to distribute on these curves here. So I take this. And let me move this out of the way. Take another join geometry node. Now you can see that the distribution happens, but let me orient it in the other direction. Maybe in this direction. Now we adjust the range a little bit. Also, let's quickly scale these down a little bit. And you can see that they scale along the line they get instanced on. But the problem here is that we have to take the previous factor in account too. So beginning with this iteration here, we have to multiply our captured attribute with our spline factor here. So yeah, let's quickly do this. I just want to create a little bit more space. Then we get the named attribute and multiply it. Yeah, and now you can see that it really nicely works. So yeah, you have to remember that the trunk gets a captured attribute of 1. Then we take the spline factor into account with the first iteration. And beginning with the second iteration, we simply take the attribute and multiply it with the factor of the previous iteration. Sounds complicated, but I hope you get the point. Okay, so let's turn this geometry we have here into a tree shape. So maybe we can start by randomizing the Z component of our rotation in this first iteration. So let me just disable the second iteration for now and remove it out of the way. Then I make a little bit more space on here. And we can randomize it really easily by using a random value node. What I like to do is I take a combine X, Y, and Z node. And here we have to remember that we are working with radians instead of degrees. So 2 pi describes the whole rotation, or simply tau. So I can type tau in here, plug this in here, and now we have this random rotation. Now to tilt all these branches, we can take, for example, a rotate Euler node, set it to local, and now with the Y component, we can tilt it. And for this, we can also take the captured parameter into account. So let me say on the bottom, we want them to be horizontal, and at the top, we want them to be more steep. But yeah, I don't want to do this in this case. So what I like to do is simply randomize this tilt a little bit. I create a new combine XYZ node. And let me take an math node. For now, I add 0 to it. So this describes the tilt we want. And to randomize it a little bit, let me make more space again. To randomize it, I take another random value node and I set it in the range of -1 to 1. I multiply it with a value which describes the strength, and I add it to my tilt factor. So here I can describe the strength, give it another seed. Yeah, so just a tiny little amount of randomness. And this is exactly what I want. So let me group all of these nodes together, put them in a frame, and maybe just color it. Like this. So this is the rotation. Next thing I want to control is the length of all of these branches. And for this I want to take into account my captured factor here. So let me make this connection. You can already see what happens. And to control the length a little bit better, we can take a map range node. And here we can define the length at the top and the length at the bottom. We can also work with a float curve, for example. And here we have even more control over the shape of our tree crown. So maybe we can make it kind of like a curvy look. And let me increase the count for now. Here we have to get a range. Yeah, you get the point. But for this tutorial, I will just work with the map range node. Let's decrease the amount a little bit. Yeah, looks good so far. And now is a good point to mention another thing I want to implement in this. So right now all these branches have the exact same thickness as the curve they get instanced on. And I want it to be controllable in another attribute. So what we can do is simply store another attribute to this and call this thickness. And let me for now say that the thickness of the first iteration is 0.5. And now we can multiply our vector we have here with this attribute. And now you can see that the trunk disappeared again. This is because we have to store this attribute here too. And let's say we leave it at 1 for now, but we can also change this. So yeah, now you can see that we can control each iteration's thickness. Okay, so now let's integrate our second iteration. So I make this connection here again. And let's have a look. You can see that all of these instances are oriented in the same direction. Let me increase the amount for now. But what I actually want is that they are aligned to the curve they get instanced on. And we can achieve this by aligning our rotation to the tangent of our distributed points here. So let me do this. Simply plugging it in the rotation won't work. We have to use the align Euler to vector node for this. And by default, it gets connected to the rotation. We have to connect it to the vector. And here we have to look which direction our curves are. They get oriented in the y direction. And now it works. We won't see it because they are oriented in the same direction. But if I change the vector here, you can see that they are kind of like getting aligned. So yeah, what we now can do is to take the rotate Euler node again, and we set it to local. And now we can control the tilt of these branches here again. And with the y component, we rotate these branches around our first branches. So we want to randomize this here again. So let me take a combine X, Y, and Z node, plug it in here. Let me, for now, just tilt it like this. Then we take a random value node again, set it to tau, so a whole rotation, plug it in the y component, and now I want to create an input for this value here. So we can again randomize it. So I simply copy the setup I have here. And plug it in here. So yeah. And again, we can work with the start and end range. So here I want to set the start range a little bit lower and the end range also a little bit lower. And maybe tilt them a little bit more. Also randomize it a little bit more, like this. Okay, so now I just steal this frame here and reuse it for all these rotation components. And now I do the same what I did in the first iteration. I simply take this value here for the scaling, make a reroute, and take a map range node to control the length. Yeah, and we can also randomize the length. But yeah, let's say in this tutorial we won't bother. Okay, so that's our second iteration here. And now we can simply duplicate these iterations and create how many we want. But first I need to store the attributes again. So here you can see that the branches disappears because they don't have the thickness attribute. So I create this. And yeah, so it should be a little bit lower than the first. So here it is 0.5. So let me say we want set this to 0.35. Yeah, looks okay. And by the way, you can create inputs for all these values. So let me say the tree is 8 meters high. And now I of course have to adjust the thickness again. Maybe we remove this multiply here. Now it looks a little bit weird, but let me take care of it. And with group inputs, we could make all of these accessible in the modifier here, but for this tutorial I won't do it. Oh yeah, let me define a thickness for the branch like this. Then we control the length of the first iteration here. I scale the thickness down. So like this maybe. And here, oops. I scale them up like this, and thickness maybe like this, or maybe even lower. And also here also a little bit lower. Yeah, looks good to me. So let's make another iteration of branches. So I simply copy this whole setup here. I want to distribute the points on this iteration here. So I connect this, make this connection again. And now let me increase the count. And to make it a little bit more visible, we can simply disable our first two iterations, so the branch and the first iteration of branches. And now can scale them down a little bit, give it a distinct seed value, also here 2. We scale down the length a little bit. Yeah. Make this connection here again. Okay, so now I want to simply adjust some values to make this look a little bit more like a tree. Okay, so let's say we are happy with the result so far. The next thing is to create a little bit of noise, because right now, obviously, the tree is very straight. So what we can do is simply add a noise here at the end, but I think it won't be very good, and I'll show you what I mean by it. So let me do this by using a set position node and a noise texture. If we plug the factor straight into the offset, it should work right away. But right now there are multiple problems, and this is because first all of our curves are consist only of 2 points, so they have not enough geometry. So we have to resample them first. So let me do this. Here what I like to do is set this to length. Now you can see that something happens. And now obviously I decrease this amount here a little bit. And to control the strength we can use the vector math scale node. Now I can scale this up a little bit. And right now the tree moves in one direction. This is because of the color information, which is in the range of 0 to 1. To solve this we can simply subtract 0.5 from it. And now it starts to work. But what I don't like about this right now is that the random positioning happens globally. So you kind of like seeing these waves appear. And I want it to be individual for each of these curves. So yeah, it's really easy to do. And what we need to do is to give each noise a random seed for each branch. And the first thing I want to talk about is how to give the noise a random seed. And this is by simply adding a random value to it, to the vector component. And by default, the vector input is the position vector. So if I plug this in here, nothing should happen. If I now add some random value to it, you can see that the noise kind of like moves a little bit. So if I just take a random value node, set it to vector, and here I just put a really high value into it and plug this in here, you can see that it really looks really noisy, and this is because every point in our tree now gets a random value, but we want the random value only for each spline. So a uniform random value for each spline, and we can get this with the interpolate domain node. Then we set it to an integer because we want an index of a spline, and we can get the index with the index node. I plug this in the value node, and now I use this for the ID input. And now each curve gets a random value node. You can see that the problem right now is that these branches are floating in the air. And this has two reasons. First, we don't want the whole branch to move the same amount. We want it to be dependent on the curve factor. So at the bottom, it should stay in place and only gets random displacement along the factor of the curve. So yeah, just take a scale node and the parameter node and plug the factor in here. And this is the first step. You can see that the trunk stays in place. And if I now move this along, yeah, you can see what happens. But still, all these branches are floating in the air. And this is because we are doing this step here at the end. But what we really want to do is we want to do it for each iteration. Yeah, so let's do this. So I create a frame out of this. Then I remove it from here. And now I do this for each iteration. So first for the trunk. So this here is my trunk. Just Let me reorder it and put a frame around this. So yeah, it would be wise to create a node group out of this here. But I won't do it in this tutorial. We have to live with this enormous node tree. And then I do the same for my branch iterations. And we have to do the noise for each iteration because, of course, the distribute points on curves node should distribute the points on the displaced geometry. Yeah, I think you know what I mean. And let's connect this here, connect this here, and also connect it to this. And the last one. Yeah. Now you can see that all my branches are connected correctly. And yeah, we can control now the strength of each iteration individually. So let's say on the last iteration there is not so much displacement, but the frequency is a little bit higher. Like this. Here I decrease the strength also a little bit and give it a higher frequency. And yeah, you can adjust it like you want it to look like. Yeah, so now you can see that it kind of looks like a tree now. And you can do so much right now. So for example, what I want to do is to give it kind of like a curve here at the bottom to have like this root structure. And also what I'd like to do is to only give the branch the high resolution. So if I toggle on this here, you can see that our curve node we have here for the profile kind of defines the resolution. And only the trunk has to have this high resolution, and the smaller here don't have to be. So yeah, maybe we can do this first. What we can do is simply exclude our trunk from this curve to mesh operator here. Maybe we put a frame around this. And duplicate it. Make this connection here again. Join geometry. And now we have two separate curve to mesh operators. And let's say for the branches, we give this a resolution of only 12. Should be enough. Now only the trunk has this high resolution. And now for the roots, we could, for example, scale the radius of our curve we have here at the bottom. So we add a little bit of curve factor to it. But what I like to do is I want to displace the mesh I have here along its normals. So let me do this. First I switch this to matcap make it a little bit better visible. And now I use the set position node, and the offset should be my normal. And here I use the scale node to control the strength. And I only want it to happen at the bottom, so we could capture our curve factor here and transfer it to my set position node. But we could also simply take the Z position. So let me show you what I mean by it. Position, separate X by Z. Here we have it. And then we scale this by the Z component. And right now the Z component obviously grows along the height. So I use a map range node. I leave it clamped because I want it only in the range of 0 to 1. And here I invert this. Here you can already see what happens. And here I can control the influence of it. Yeah. And I have an idea instead of using the normal, which leads to this tilted look here, because yeah, it is a little bit tilted here at the bottom. We could use instead the position and we normalize it. So normalize and use this. So let's have a look. Doesn't work. Maybe if we exclude the Z component from it. So take another multiply node, multiply each component by 1 except Z. Yeah, works a little bit better. So maybe we leave it like this. Oh yeah. You have to choose the method dependent on what you want. So yeah. And maybe it is a little bit cleaner to simply store the factor of this curve here instead of using the Z position. So yeah, let's do this. So I kept using capture attribute. And I want to store the float, the factor. Now I have it stored here, and I can use this instead. And now I obviously have to redefine this range here. Yeah. So now to give it the nice curvy look, we could either change this here to another interpolation method. So stepped, smooth step, etc. But what I like to do is to set this to 1 for now and linear. Then I use the power math node and set the exponent to 2. Now we have this really smooth curve here at the bottom. And this is similar to what happens if we use a float curve and give it this curvy look, but it's only described in math, so yeah. Should be a little bit more performant and a little bit better to control. So yeah, now to control the strength, we could use a multiply node. Maybe like this. And the cool thing now is that we can use a noise texture. and use the factor for the strength here. So maybe like this. And also I want to remap this value again to give it more contrast. It's kind of like using a color ramp, but yeah, I tend to use the map range node more often. So here we can control the contrast of it. And now it has this a little noisy look. And the trick now is to simply scale this texture a little bit. So for example, you can already see what happens if we do this. Yeah, kind of look like the bottom of a tree now. So this here is the setup for my roots. Now I make this connection here again. And now I decided to just make one attribute or parameter available in my geometry nodes here. And this is the seed, simply to switch between different variations of this tree. So I will do this quickly. And here I delete the geometry input because I don't need it. Seed, give it a default of 0. And now for each seed in my geometry node tree, I will add a random value to it. And this is because I don't want each random value to have the same seed. So I use an add node and just add some value to it. And lastly, I will create a random seed for my noise texture here. So again, I use a vector math add node and add a random vector to it. And you can see that it is individual for each vertex, for each point. And we take care of it in a minute. So what we can do is either give it a uniform ID value, so an integer example, or we can take the mesh island, because right here we are working with a single mesh island, and take the mesh island index. And this should do the trick. So yeah, here we can create another random seed. Yeah, I really like the setup so far. The next step would be to distribute some leaves on these branches. And this is, yeah, really simple, but there are multiple methods on how to do this. So let me quickly explain the first method. And this is just distribute some leaves on these curves here. So we can take our distribute points on curves node, and here I distribute some points with a really high point count. And let's say we want to instance some planes. So take a grid with a resolution of 2 by 2. And now I want to randomize the rotation. So I take a random value node and set it to vector. Now I put tau in all of these 3 components here. Rotate it randomly. And let's take another random value node. We leave it at float for now and plug it in the scale. And here I can control the scale of these. And let's have a look what this looks together. Yeah, like this. But here you can see that the center of all these planes is in the middle. But let me offset it a little bit. So here, my grid. I take a set position node. And let us offset it in the x direction by 0.5. And now we can use this for the instance. And let's have a look. Yeah, now you see that it is placed a little bit better. So yeah, now let's adjust this here a little bit. Maybe like this. And here we have to put a really high count to give it enough geometry. Okay, so now let me start by adding some materials. So first I make a frame around this. And also I realize my instances. And then I open a shader node editor. Okay, so first we need 2 materials. So the first one is the tree bark. And the next one are my leaves. We apply the leaves material to the leaves. So set material. And the rest should have the bark material. Now I set this to rendered view. I simply add some lights to the scene. Just a very basic setup here, nothing too special. And just work with very simple materials for this tutorial. So for the bark, I use a noise texture. Let's have a look. I increase the scale a little bit. And I also want to stretch it along the Z component, maybe like this. Yeah, it looks okay. Then I use a color ramp to define the colors. Or let's say the dark areas should have maybe like this. And then the lighter areas like this. This is the color input. Then it should be pretty rough material. And for the normal map, I use a bump node. Plug the noise in the height. Let's have a look. I decrease the distance. And yeah, that should work. And yeah, now we have a very, very simple tree bark. So I decrease the strength a little bit more. And there's a little problem right now. This won't be too much of a problem, but here at the branches you can see that the mapping of the noise is based on the generated coordinates, which are really simple, similar to the object coordinates. I tend to use the object coordinates more, but now I have to scale this down a little bit. And to transfer coordinates to the shader, we could create our UVs in our node tree here. And for this we can, for example, use the UV nodes, the dedicated UV nodes. But we can also capture the factor of these curves. So the curve we have here, the curves we have here, and also the profile curve, and then combine them to coordinates. But I think this would be a little bit overkill for this tutorial, because then the node tree gets even more complicated than it already is. And maybe that is a topic for a separate tutorial. So yeah, just let me work with what we have here, because I think for most cases this would be totally okay. Okay, yeah. So next would be the leaf material, and here we have to unwrap them. So this is my grid, and I simply store the position on it. So I could use the unwrap UV nodes we have, but a simpler method would just be to store the position. And I call this simply coords for coordinates, set it to vector, and use the position. And here in the material, I get this attribute. And I made a little mistake here. And I want to store the attribute before I offset the grid. So let me do this. Now just pick a plane. So yeah, you can see what the coordinates look like. And to create a really simple leaf material, just separate these components. And then let me have a quick look where we are at. Yeah, I want to take the y coordinate and create the absolute from it. And then I compare it with my x component. And yeah, you can, for example, use greater than. And I want to remap my x component so it is in the range of 0 to 1. And right now it should be in a range of minus 0.5 to positive 0.5. So I can simply add 0.5 to it. Or maybe I am wrong and it was before in the range of minus 1 to 1. So yeah, instead let me take a map range node and have a look. It's really doesn't matter so much. So yeah, let's create a shape with a float curve node, and here we can define our leaf shape. Maybe like this. And instead of using a greater than node, we could, for example, use a subtract node. So yeah, that should be enough. Now I switch the blend mode to alpha clipped, because now I can take a greater than node set it to a really low value, maybe 0.01, and use this for the alpha input. Shadows, I will use alpha clip for now. Now it takes a while to compile, and you can see that we now have this alpha applied. And for the color, I can use this. And of course, I can take a color ramp and define some colors for it. So yeah, really no rocket science here. Just a simple, very simple leaf shader. Yeah, so now let's increase the leaf amount a little bit more, make it more dense. And also I want to give the branches more length, because right now it looks a little bit weird in my opinion. So like this. And now comes a really cool trick which I've used in my career as a technical artist in game design quite often. And this is transferring normals to the leaves, because right now the shading is kind of cluttered, and to give it more of a smooth look, we can transfer custom normals to these leaves. And this gives the typical stylized look to trees in games. Oh yeah, let's do this. So for this, I simply make more space here. I disable everything except the leaves. Okay, so here we have our basic leaf geometry. And now we can, for example, just take these points we have here and randomize them a little bit in their position. So set position and random value, set it to vector -1 to 1 in combination with a scale node, and use this for the offset. And you can see we randomize the position a little bit. And now we turn these points to a volume and this volume to a mesh. So points to volume and volume to mesh. And now we can adjust this a little bit. Give it more geometry, maybe 80. And we set the smooth, because we want smooth normals. And now we have this weird geometry here. And here we have our leaves. And we want to transfer the normals of this geometry to our leaves. So let's do this. We can do it with the transfer attribute method. So for this we need the sample nearest. We want to sample this geometry here. And then we need the sample index node, because here this gives us the index of the nearest surface. We want to sample a normal, which is a vector. The geometry is the same geometry we have here. And now we want to store this on our leaves. So we use a store named attribute, call this normal, plug this in here, but set this to vector first. And now we have stored this attribute. And in our shader, we now can take this attribute if we have a look at it, you can see kind of looks like normals. So in comparison with the default normals, which is really cluttered, it looks like this. Yeah. So now if we plug this normal in here, it should look a little bit smoother. So yeah, without and with this normal, looks a little bit fluffier in my opinion. Oh yeah, let's connect these again. Okay, so now I think it's a good moment to wrap this tutorial up. We could include even more functionality in this tree, but I think the tutorial is long and complex enough. So yeah, we could, for example, include pruning, or yeah, like the UV unwrapping and so on. So there are infinitive possibilities to this. Could create some wind simulation, give it more complex shaders. Yeah, it's an endless rabbit hole of possibilities. So yeah, I think that's enough for now. I hope you liked this tutorial and see you next time.